So now, what do I mean by wave shaping circuit? So wave shaping circuit is nothing but those circuits which are used to alter the shape of the waveform. Okay, so what type of waveforms are we using? They can be a sinusoidal wave or it can be a square wave. Then what do I mean by shaping of the waveform is, for example, if I take the waveform as a sinusoidal wave, okay, so if I'm able to get an output something like this for this type of waveform. So what is that I'm doing? My input waveform here has positive and negative half cycles, but output waveform has only one half cycle. Or let us say, if you are having a waveform something like this, which means input has both the half cycles, but output is having only complete negative half cycle and a portion of positive half cycle. So that means the peak is being clipped off here. There is no peak waveform. Okay. So this is what is meant by shaping of the input waveform. So instead of the complete cycle with positive and negative half cycles, we see that in the output of the wave shaping circuit, there is a portion of output being absent. So such type of circuits we call them as wave shaping circuits. Such type of circuits we call them as wave shaping circuits. So now, if you see, these wave shaping circuits basically come under two categories. Okay, these wave shaping circuits basically they come under two different categories. So one we call it as linear wave shaping and the other one is called as non-linear wave shaping. Okay, so the first type of wave shaping circuits we have is linear wave shaping circuits, and second one you have is non-linear wave shaping circuits. Now the question is, on what basis are you defining this linear wave shaping circuits and non-linear wave shaping circuits? So the definition or the difference we are using to give this linear or non-linear is based on the type of devices that these circuits are using. Okay, it's based on the type of devices. So if the circuit is using a linear device, it is called as a linear wave shaping circuit. If the circuit is using a non-linear device, we call it as non-linear wave shaping circuit. Now the question is, what do I mean by non-linear devices and what do I mean by linear devices? So it is very simple. If the devices are exhibiting linear portion of the characteristics, they are called linear devices. If the device is exhibiting non-linear characteristics, we call them as non-linear devices. Okay, so for example, if you take the devices which gives linear characteristics, like we can call them as capacitors, okay, inductors, all these are come under or they come under linear devices. And so if the linear wave shaping circuit uses these type of devices, we call it as linear wave shaping circuit. So resistors, inductors, capacitors, such type of aura, even op-amps, okay, operational amplifiers. So if these type of devices are used as a part of a circuit, we call them as linear wave shaping circuits, and these devices we call them as linear devices. We call them as linear devices. So the circuit built up using linear devices are linear wave shaping circuits. Then what comes under non-linear devices? So we said that non-linear wave shaping circuits are those circuits which use non-linear devices. What are those non-linear devices? Example, diodes. Okay. Then you have transistors like BJT, FET. Okay. All these are non-linear devices. So if the circuit is using non-linear devices like diodes, transistors, etc., we call them as non-linear wave shaping circuits. So among these two wave shaping circuits in our syllabus, we will be discussing about what is called as non-linear wave shaping circuits. What are they? Non-linear wave shaping circuits. Now, in this non-linear wave shaping circuits, I said we have two devices. One is diode and the other one is transistor. So that means again this non-linear wave shaping devices are circuits are classified into two types. They are called as diode wave shaping circuits, or we call them as diode clippers. Okay, and the second one we call them as transistor. Okay, we call them as transistor clippers. So that means, to say in simple, your non-linear wave shaping circuits, they are categorized as diode clippers and transistor clippers. So together, okay, we call them as clipping circuits. together, we call them as clipping circuits. Or to say in another way, these non-linear wave shaping circuits are basically categorized into two types. One is clipping circuits, and the second one we have it as the clamping circuits. The second one we have it as clamping circuits. So to say in simple, by using these non-linear devices like diodes and transistors, you can develop by using these non-linear devices. So here these are non-linear devices. So using these non-linear devices, diodes and transistors, you can develop two types of clipping circuits or non-linear circuits, which are called as clipping and clamping circuits. Okay, so it is about these non-linear wave shaping circuits we are going to discuss in detail. Clear? So whether it is clipper or clamping circuits, they come under basically wave shaping circuits. In this wave shaping circuits, you have two types. One is linear, the other one is non-linear. So this classification of linear and non-linear is given based on the type of devices we are using. So this type of devices are categorized once again as linear and non-linear. Linear devices examples are resistor, capacitors and op-amps. Non-linear devices are diodes and transistors. So if the circuit is using these type of devices, we call the respective circuits as linear wave shaping circuits and non-linear wave shaping circuits. So in this non-linear wave shaping circuits, again, you have two types. One is clipping and clamping circuits, which use these non-linear devices, which are diodes and transistors. Okay. Is this clear up to this? Clear?
Yes, ma'am.
Okay. So now once this is clear, now let us move into the different types of non-linear wave shaping circuits. Okay. So non-linear wave shaping circuits. So what are the types of non-linear wave shaping circuits?
Clipping and clamping.
Yes, they are nothing but clipping and clamping circuits. So first one we have is clipping circuits. And second one we have is clamping circuits. So what do I mean by a clipping circuit? That is what first we will be discussing. And in this clipping circuit, what is that we said? It is a wave shaping circuit. Clipping circuit is nothing but a wave shaping circuit which controls, okay, which controls the output waveform, which controls the output waveform by removing, okay, which what does it do? Controls the output waveform by removing or clipping. What is it? By removing or clipping a portion of the applied wave. By removing or clipping a portion of applied wave. What do I mean by applied wave? I mean by applied wave as nothing but the input. So whatever the input waveform you are applying, in that input waveform, it is trying to remove a portion of it. Okay, it is going to remove a portion of it, and such a type of wave shaping circuit, we call it as clipping circuit. Now, if you look at the clamping circuit, okay, clamping circuit is nothing but again a wave shaping circuit which clamps, okay, or we say restores, okay, which clamps or restores the input waveform, which clamps or restores the input waveform to another level, to another level. Such type of circuit we call it as a clamping circuit. Okay, so in this clipping or clamping circuits, what are the devices we will be using? They are nothing but non-linear devices. What are the examples of non-linear devices we specified?
Diodes,
So they are
transistors.
diodes, okay, like both PN junction diode or Zener diode, transistors such as BJT and FET. So those wave shaping circuits which use non-linear devices, we call them as non-linear wave shaping circuits, and they are of two types, clipping and clamping. And the non-linear devices we use are diodes and transistors. Okay, so now if the Circuits are using diodes. We call them as diode wave shaping circuits. If you are using transistor, you call them as transistor wave shaping circuits. Now with this introduction, now let us look into the first type of wave shaping circuit, which is nothing but clipping circuits. Now I already said that clipping circuits can use diode as well as transistor, right? So if you use a diode as a nonlinear device, we call it them as what? If in the clipping circuits, you are using diode as the nonlinear device, we call them as diode clippers. If in the clipping circuits, if you are using transistor as the device, you call them as transistor clippers. Okay, so clipping circuits can be built using a diode and a transistor, and so respectively named as diode clippers and transistor clippers. But in our syllabus, we will be talking about what are called as diode clippers. Okay, we will be talking about diode clippers. So how to define these diode clippers now? All what we have discussed till now, if you put it into a single sentence, we can give the definition of diode clipper. How? Diode clippers are nothing but wave shaping circuits. Okay, or diode clippers are non-linear wave shaping circuits where diode is used for clipping purpose. Where diode is used for clipping purpose. Okay, so now again, if you want to see, these diode clippers are further categorized into two types. Okay, we can call them as series clippers or shunt clippers. We can categorize them as series clippers or shunt clippers. Based on what parameter we categorize this as series and shunt. So this categorization of series and shunt is dependent based on the diode position or how we are connecting the diode in a circuit, whether it is in series or in shunt. Based on diode position, you decide whether the clipper is called as a series clipper or a shunt clipper. Again, if you look into further, this series clipper is further categorized into positive clipper and a negative clipper. Okay, these are further classified into positive clipper and a negative clipper. Likewise, shunt clippers are again categorized into positive clipper and a negative clipper. So thus, if you look into the types of clipping circuits, you end up with two types of series clippers, two types of shunt clippers. Now the question is, on what basis are we giving the classification as positive or negative? So we are giving this classification as positive or negative based on again the diode, but now it is not diode position, but now we say it is based on diode orientation. Okay, based on diode orientation. What do I mean by orientation? In one case, I can connect a diode anode first and cathode next. Or else if I alter or reverse the position of the diode, this is how I have. So this is what I mean by orientation of the diode, based on how the anode and cathode terminals are connected. When you say diode position, you can have this diode in the series arm or you can have the diode in the shunt arm, like this. Okay, it can be like this. It can be in the series arm or shunt arm. Fine. So based on this, you have the diode either in series or in shunt or positive as well as negative. Is that understood? The types of diode clippers?
Yes, ma'am.
Okay. So now let us move to the next one. What is that? It's talking about each of these clippers. Okay. So now first let us look into the series clippers and then we will move on to the shunt clippers. Okay. So first one, let us talk about the series clippers. Okay. Let us talk about the first one, which is called as so when do you call a clipper as a series clipper?
By the diode position.
diode position. Now the question is, what are the different components that I connect in a clipping circuit? Okay, what are the different components that we connect in a clipping circuit, whether it is a series clipper or a shunt clipper? What are the components that we usually connect in a clipping circuit? So remember, any clipping circuit will have first the clipping device. What is the clipping device? It's nothing but a diode. Okay, it will have a voltage source because we need to apply the voltage. It has a voltage source, and then finally it have a resistor, or it has a resistor. So these are the three components that we usually find in any clipping circuit. Okay. So these three components, they will be connected either in series or in parallel based on what type of clipping waveform we need. Okay. So let us see how do we have these three components arranged in a series clipper. Okay. So since I said it is a series clipper, what is that we need to have? We need to have this particular diode connected in series where to the load. So, okay. So this is how you can have the circuit diagram as. Sorry. So this is the diode that is in the series arm connected in series to the load resistance. And this resistance is what we call it as the load resistance RL. This is represented by diode D. And I said voltage source, right? So that voltage source is what we apply here as input. So we call it as input voltage. And based on the input voltage and based on the state of the diode, we try to get the output voltage. And this output voltage will be measured across the load resistance RL. So here if you see, the diode is connected in series to the load. What is that? The diode is connected in series to the load. So we call it as a series clipper. Now we said that we have again in series positive and negative clippers. So how do we decide whether this circuit is an example of a positive series clipper or a negative series clipper? Let us see by understanding how this circuit works. So to understand the circuit, remember always in clipping circuits, the input we are going to give is always a sine wave. Okay, you can also use a square wave, but to understand easily and clearly, in all the clipping circuits, we use the input waveform as a sine wave, and these are the different components that we are going to use. So these are the things that you should always remember for a clipping circuit. Fine. Now with this input, let us now analyze this circuit. So how is that this circuit? Let us say this is the input waveform which we are applying to the circuit. And let us say this input we are showing the y-axis by its parameter, and x-axis let us take the angular time period omega t. Now this is 0 and here the positive half cycle length. So let us say pi, and here the next half cycle length. So let us say 2 pi. So I have taken one input cycle for 0 to pi period as positive half cycle and pi to 2 pi as negative half cycle. Okay. And this is diode D. And here one important thing that we always consider is we are assuming that the diodes we are using are nothing but ideal diodes. Okay, we are not taking practical diodes into consideration. We are taking the type of diodes as ideal diodes. That is what we are assuming here. Okay, we assume that the diodes we are using are ideal diodes. The reason is very simple. Why? What is the difference between practical and ideal diodes? Can anyone say?
Practical diodes will varies with the temperature, and
Ideal diodes?
it is the assuming of our for our comfort.
Okay, fine. But the basic difference between ideal and practical diode lies with respect to the V gamma. So your ideal diodes doesn't need the concept of V gamma to enter into conducting state when voltage is given. Whereas practical diode doesn't enter into conducting state till V gamma, right? Yes or no?
Yes, ma'am.
So only when I have 0.6 volts for silicon or 0.2 volts for germanium, till that point of time, we don't have the diode entering into on state. Only after your applied voltage V in, Okay, after your applied voltage Vin greater than these two voltages, then only diode enters into on state. Whereas in case of ideal diodes, there is no concept of this. As soon as they apply the voltage, I see that the diode enters into conducting state. This is what we see in the characteristics, right? Isn't it? So this is the reason why we assume that our diodes here are ideal diodes, just for easy understanding. Okay, if V gamma is there, then the output waveform is going to alter a little bit. Okay, so initially to understand very clearly the clipping operation, we assume that the diodes are ideal in nature. Okay, so with this, if we see that the input waveform is given by, as it is shown here. Okay, as it is shown here. So how do we have the output waveforms? We need to analyze. So remember, whenever it comes to the analysis of this clipping circuits, you need to split your input waveform into two. What are they? If you see, this is the positive half cycle and it has a negative half cycle. So if you want to give the analysis for this clipping operation, you need to consider or split your waveform. For positive half cycle, what is going to happen? And for negative half cycle, what is going to happen? So if you are able to analyze your input waveform for both these half cycles, then you can know what is the output. Okay, so first let me take the case of positive half cycle. What do I mean by positive half cycle? For example, if you take, it is starting from 0, then it is going to the maximum value, right? It is going to the maximum value. What is the maximum value it is going to? Anyone?
VM.
Yes, it is Vm. So that is what usually we assume, right? So this is Vm, positive value. Then reaching to 0, again entering into negative half cycle, reaches a maximum value of minus Vm in negative half cycle, then drops to 0. And this is one complete cycle. If I assume my input is continuous in nature, you have multiple cycles followed by this. But since it is a sine wave and repetitive in nature, it is the same as for one complete cycle. So we analyze the operation of this clipping circuit for one complete cycle. So if you are able to do it, the same output will be replicated for all the other cycles as well. Okay, so that's the reason why we have taken for one half cycle at a time, one positive and one negative, and we are going to analyze this. So to understand this for one half cycle, okay, let us take first the positive half cycle. So what is that your positive half cycle has? Something like this. So it is starting from 0, okay, reaching to a maximum value and then coming to 0. Anyhow, I assumed this diode is an ideal diode, so there is no concept of V gamma, that is V gamma is 0 volts. So what happens? As soon as this diode is receiving the input, the diode will either enter into on state or off state. Whether it is on or off, that depends upon what type of input it is receiving, the diode is receiving, right? So how do I justify that? I know that this is P, this is N, which means this is anode and this is the cathode. Now, when do our diode enters into on state? When anode is receiving positive voltage or negative voltage?
Positive voltage.
Positive voltage, right? So I am analyzing this circuit initially for what cycle? Positive half cycle. So any value greater than 0 is a positive voltage, right? So instead of taking for each and every value, what we do is we analyze it for the maximum value. So if it is applicable for maximum value, it is equally the same for all the other voltages, right? Because all are positive voltages, any value greater than 0. So when you say positive voltage, positive here, negative here, and your input is changing like this. So for this positive half cycle as input, positive voltage is received by the anode of the diode. And so what is the state of this diode?
Forward.
Forward bias. So what is the diode under forward biased condition?
Exponential increase in
No, it is in conducting state or non-conducting state.
conducting state.
So you see that for positive half cycle as input, you see that the diode is in conducting state, the diode deconducts. Now, when the diode is in conducting state, I can say that it is also in on state, isn't it? Diode conducts means it is in on state. Yes or no?
Yes, ma'am.
So when diode is in on state in the circuit, how can we replace it by
Short.
short circuit? So this is going to be a short circuit. So diode is in on state, so I replace it with a short circuit. Now this is RL. Now finally, what is important for me to measure what is this output voltage V0, right? So when positive half cycle you have given, which is varying in nature, RL is already a value known for us, which is fixed value. And for this voltage, diode is entered into short circuit. So what about the current flow in the circuit? Will current exist or not?
Exists.
So that means I say simply current I flows in the circuit, right? And this current I also passes through the load resistance RL. So when this I passes through load resistance RL, what happens to V0?
Decreases.
Which means V0 exists, isn't it? V0 exists.
Yes, ma'am.
So what is that I can say? When diode is in on state, that is, it is replaced with a short circuit. I also say that current flows in the circuit, isn't it? Current flows in the circuit, and that too, it flows through where? It flows through RL. So when I flows through RL, we see that V0 is developed. What is the equation for this V0? V0 is what? Output voltage
I
across
into
the load
RL.
resistance. Yes, it is I into RL. Very good. It is I into RL. So that means for positive half cycle as input, okay, what is that? For positive half cycle as input, I could see that output voltage V0 is existing. But now the question is, what is input I know? What is it? It is a positive half cycle, isn't it? Which is starting from 0, slowly increasing, going to the maximum value and then dropping again to 0. But what is my output going to be? Is it a straight line or it is 0? Or on what parameter does it depend on? So to understand that, you need to go through this equation clearly. What is that you see? We see that V0 is proportional to I and RL, isn't it? But I know that RL is a fixed value. How I am saying RL is a fixed value? When I am designing this circuit itself, I am going to take, for example, RL, let us say 1 kilo ohms or 100 ohms, 500 ohms. So some value we take here for RL, which is fixed. So RL is not changing, which means the output voltage V0 should finally depend on what?
RL.
I. Now, I is depending on what parameter? I is
V.
depending on Vin, isn't it? As how the input voltage is changing, accordingly I is also changing. So let us say if the input voltage is starting from 0, going maximum and then becoming 0, I also see that I also starts from
0.
0. Then what happens? Goes to the maximum value and again it drops to 0. Now, this is what I see for Vin, isn't it? This is what I see for Vin. This is for I. Now, what did I say? V0 if I plot it here. My V0 is depending on I because RL is fixed. So what happens now? Your V0 also follows how I is changing, which means that simply V0 is directly proportional to V. So how the input waveform is changing, accordingly output waveform is also changing. But how is that we are observing that? It is through I. Okay. So now we said V0 is existing, but how is it? It is similar to our output voltage, sorry, input voltage VI. Clear up to this?